Welcome to MSN Digit Max. I am Shubha, Assistant Professor, Department of Mathematics, Madurai Sivagasi Nadas, Pioneer Meenakshi Women's College, Puvandi. Here is a learning resource for Abstract Algebra, Unit 1, Module 8. In the previous videos, we covered the topics definition for groups and examples for groups. In this video, we will see abelian groups and elementary properties of a group. Let me start with the definition for abelian groups. A group G is said to be abelian if AB equal to BA for all A comma B belongs to G. A group which is not abelian is called non-abelian group. Here, we have to check for the group G the additional property AB equal to BA. If it satisfies the condition, then it will become abelian group. It does not satisfy the condition, it will become non-abelian group. Let me see some examples for abelian and non-abelian groups. For this, we already proved several examples for groups. Let me check that group will become an abelian or not. Let me take the simplest example of a group Z comma plus, that is Z under addition. For this group A plus B equal to B plus A, therefore Z comma plus becomes an abelian group. Likewise Q, R and C under the usual addition, they are also abelian groups. Example 2, P of S comma delta. P of S is the power set of S and delta is the symmetric difference of two sets. That is A delta B is equal to A minus B union B minus A. Then B delta A also equal to B minus A union A minus B. Both are equal. Therefore, it satisfies the property of abelian group. Hence, P of S comma delta is an abelian group. Example 3. Here we take the set B of R, the set of all bijections from R to R. Then B of R is a group under composition of functions. This example is an example for non-abelian group. That is, it does not satisfy the property of abelian group. Therefore, we take two elements from B comma R, that is F from R to R and G from R to R. They both are defined by f of x equal to x plus 3 and g of x equal to 2x. Here we have to check the property for abelian. For this, let me first prove that both f and g belongs to B of R. To prove f is 1, 1, let me start with f of x equal to f of y, which will imply x plus 3 equal to y plus 3, which implies x equal to y. To prove f is onto, we start with the element y belongs to R. Then we can find a pre-image, that is y minus 3 belongs to R. Therefore, f is both 1, 1 and onto. Therefore, f belongs to B of R. Likewise, for g also, we have to check the two properties 1, 1 and onto. To prove g is 1, 1, g of x equal to g of y, which implies 2x equal to 2y, which implies x equal to y. Therefore, g is 1, 1. To prove g is onto, take y belongs to R, then we can find an inverse element y by 2 which belongs to R. Therefore, g is onto. Then G is also a bijection. Now we can find f composite G. F composite G of x is equal to f of G of x, which is equal to f of 2x, which is equal to 2x plus 3. And find G composite f of x equal to G of f of x equal to G of x plus 3 equal to 2 into x plus 3, which is equal to 2x plus 6. Therefore, F composite G not equal to G composite F. Therefore, this B of R does not satisfy the property of abelian. Hence, B of R is non-abelian. Then, example 4. Zn, plus circle is an abelian group. Let A, B belongs to Zn. Let A plus B equal to Qn plus R, where 0 less than or equal to R less than n. Then A plus circle B equal to R, and also B plus circle A equal to R, because both A plus B and B plus A equal to Qn plus R. Hence, both the values are equal. That is, A plus circle B equal to P plus circle A. Hence, Zn, plus circle is an abelian group. Then example 5. Let me take the set G equal to set of all A, B such that A belongs to R star, B belongs to R. Then define star as A, B star C, D equal to AC, BC plus D. We already proved that this G, star is a group. Now we are going to prove this G, star is non-abelian. That is, it does not satisfy the property of abelian. For this, we have to take two elements from G. Let me choose one example. 2, 3 and 4, 5 belongs to G. Let me find out 2, 3 star 4, 5 equal to, from the definition of star, we get 2 into 4 equal to 8 and 3 into 4 plus 5 equal to 17. Therefore, the answer is 8, 17. Likewise, we have to calculate 4, 5 star 2, 3 equal to 4 into 2, 8, 5 into 2 plus 3 equal to 13, which will give you the answer 8, 13, but both are not equal. Therefore, this G does not satisfy the property of abelian. Therefore, G is non-abelian. Next, example number 6. The set of all 2 by 2 non-singular matrices A, B, C, D, where A, B, C, D belongs to R, is a group under matrix multiplication, and this is non-abelian. The set of all 2 by 2 non-singular matrices under matrix multiplication. This set, we already proved that it will become a group. Now we are going to prove this is not abelian. For this, we have to do two elements from the set. Let me take the matrix 2, minus 1, 4, 3 and the matrix 4, 0, minus 5, 2. Let me multiply those two matrices. Matrix 2, minus 1, 4, 3 into matrix 4, 0, minus 5, 2 equal to the matrix 13, minus 2, 1, 6. Let me calculate the matrix 4, 0, minus 5, 2 into the matrix 2, minus 1, 4, 3 equal to the matrix 8, minus 4, minus 2, 11. Here both the matrices are not equal. Therefore, the matrix multiplication does not satisfy the property of abelian. Therefore, this set is not abelian group. Example number 7. Q star, R star and C star. They are all abelian groups under usual multiplication, because these three sets satisfy the property AB equal to BA for all A, B belongs to Q star, R star and C star. Let me move on to next example. Example number 8. Let n be a prime. Zn minus singleton 0 is an abelian group under under multiplication modulo n. Let A, B belongs to Zn minus singleton 0. Then AB equal to Qn plus R, where 0 less than or equal to R less than n. From this definition, we know that A dot circle B is equal to R. Similarly, also we can find B dot circle A, which is also equal to R. Since B into A also equal to Qn plus R, therefore we get the result B dot circle A is equal to R. Therefore, this dot circle becomes commutative. Therefore, Zn minus singleton 0 is a abelian group under multiplication modulo n, where n is a prime. Next, we will see elementary properties of a group. Theorem 3.1. Let G be a group, then the identity element of G is unique. Number 2. For any A belongs to G, the inverse of A is unique. In this theorem, we are going to prove identity element E is unique and the inverse element A dash is unique. To prove this, let me start with two identity elements, that is E and E dash be two identity elements of G. Suppose E is an identity element. Then from the definition of E, we get the property E dash equal to E dash E equal to E dash. Suppose E dash is an identity element, then E dash satisfies the property of identity, then we get E dash equal to E dash equal to E. From these two relations, we clearly see that E equal to E dash. Therefore, in a group, there will be only one identity element. Number 2. To prove number 2, for any A belongs to G, I am going to choose two inverse elements, that is A and A dash are the two inverse elements for A. Suppose A dash is an inverse of A. Then from the definition of inverse, A dash equal to A dash A equal to E. Suppose A double dash is an inverse of A. Then by the definition of inverse, A double dash equal to A double dash A equal to E. From the above two equations, we simplify that A dash equal to, let me write A dash as A dash into E. For E, we have to substitute A double dash. Then use associative property, we get A dash A into A double dash. Now A dash A becomes E. Then E A double dash is equal to A double dash. Therefore, A dash equal to A double dash. That is, for any element in G, there will be only one inverse for that element. From this theorem, we note that the inverse of A can be written as A inverse. That is, the notation is A power minus 1. Let me move on to next property, theorem 3.2. In a group, the left and right cancellation laws hold. The laws are AB equal to AC implies B equal to C, and BA equal to CA implies B equal to C. That is, we are cancelling the leftmost elements or the rightmost elements. To prove this, let me start from AB equal to AC. From theorem 3.1, we already proved that for any element A, there is an element A inverse. Therefore, we pre-multiply that A inverse on both sides. We get A inverse into AB is equal to A inverse into AC. Then use associative property, A inverse A into B equal to A inverse A into C, which implies E into B equal to E into C, which implies B equal to C. Therefore, from AB equal to AC, we proved that B equal to C. That is, left cancellation law is true. And then number 2, let me start from BA equal to CA. Here we have to post multiplying by A inverse on both sides. We get BA into A inverse equal to CA into A inverse. By using associative property, we get B into A inverse equal to C into A inverse, which implies BE equal to CE, which implies B equal to C. That is, right cancellation law true. Hence, we prove both cancellation laws are true in a group G. Next property, theorem 3.3. Let G be a group and A comma B belongs to G. Then the equations Ax equal to B and Ya equal to B have unique solutions for X and Y in G. To prove this theorem, we consider an element A inverse B belongs to G. Then, from the given equation Ax equal to B, we take the left hand side Ax equal to A into A inverse B equal to A inverse into B equal to EB equal to B. That is, in the equation Ax equal to B, we substitute for x A inverse B, which satisfies the given equation. Therefore, x equal to A inverse B is a solution for Ax equal to B. Then we are finding the solution for x. But we are going to prove this solution is unique. Therefore, let me take two solutions for Ax equal to B. Let x1 and x2 are the two solutions for Ax equal to B. Then Ax1 equal to B and Ax2 equal to B. On simplification, we get Ax1 equal to Ax2, which implies x1 equal to x2 because the left cancellation law is true in G. Therefore, we get x1 equal to x2. That is, the solution must be unique. Hence, x equal to A inverse B is the unique solution of Ax equal to B. For the next equation, Ya equal to B, we have to take an element B A inverse. Then Ya equal to B A inverse into A equal to B into A inverse A equal to BE equal to B. Therefore, the element Y equal to B A inverse become the solution for Ya equal to B. Here also we have to prove the uniqueness. For this, let me take two elements y1 and y2 are the solutions of Ya equal to B. Then y1 A equal to B and y2 A equal to B. By using right cancellation law, we get y1 equal to y2. Therefore, y equal to B A inverse is the unique solution of Ya equal to B. Hence, we proved the property 3, that is theorem 3.3. Next comes property 4, theorem 3.4. Let G be a group. Let A comma B belongs to G. Then AB the whole inverse equal to B inverse A inverse and A inverse the whole inverse equal to A. To prove this, AB the whole inverse equal to B inverse A inverse. That is, we are going to prove the inverse of AB is B inverse A inverse. Therefore, we have to calculate AB into B inverse A inverse. Use associative property A into B inverse into A inverse equal to, use identity property A inverse equal to A inverse equal to E. Similarly, B inverse A inverse into AB equal to B inverse A into B equal to B inverse EB equal to B inverse B equal to E. Therefore, the inverse of AB is B inverse A inverse. Therefore, AB the whole inverse is equal to B inverse A inverse. Number 2. A inverse the whole inverse equal to A. That is, inverse of A inverse is A. But we all know that inverse of A is A inverse. Then we have the property A inverse equal to A inverse A equal to E. From the same property, we will get the result. Inverse of A inverse is also A. Hence, A inverse, the whole inverse equal to A. From this property, we get A1, A2, etc. An. That is n elements from G. We are getting that A1, A2, etc. An, the whole inverse also can be written as An inverse into An minus 1 inverse into etc. A2 inverse into A1 inverse. To move on to next property, we define a new term, that is, let G be a group and A belongs to G. Then for any positive integer n, we define A power n is equal to A into etc. A n times. That is, A power n can be written as multiplication of A n times. Likewise, the inverse of A power n can be written as A power n, the whole inverse is equal to A inverse the whole power n. Also, we define A power 0 equal to E. Therefore, A power n can be defined for all integers n. And then notation. Suppose the binary operation on G is plus. We denote the same definition as A plus A plus A n times. This can be written as n A. Therefore, for plus, we have to use NA. For multiplication, we have to use A power n. From these two definitions, we are going to prove the property number 5, theorem 3.5. A power m, A power n equal to A power m plus n. Second one, A power m, the whole power n is equal to A power mn. Both m comma n belongs to Z. Let me prove the first property. We are going to prove the first one by induction on n. When n equal to 0, the result is trivial. Let me take n greater than 0. Let me start from n equal to 1. When m greater than or equal to 0, A power m plus 1 is equal to A power m into A power 1. When m equal to minus 1, A power m plus 1 equal to A power minus 1 plus 1 equal to A power 0. From the definition itself, A power 0 equal to E. A power m into A power 1 is equal to A power minus 1, A power 1, which is equal to E, because A inverse A equal to E. Therefore, A power m plus 1 equal to A power m into A power 1. Suppose m less than or equal to minus 2. Therefore, let me take m as minus p, where p is greater than or equal to 2. Then A power m into A power 1 equal to A power minus p into A, which is equal to A inverse the whole power p into A, which is equal to A inverse the whole power p minus 1, A inverse into A. Therefore, we are getting that A inverse the whole power p minus 1 into E, which is equal to A power minus p plus 1, which is equal to A power m plus 1. Hence, A power m plus 1 is equal to A power m into A power 1. It is true for all m belongs to Z. Therefore, the result is true for n equal to 1. By induction, we are assuming that the theorem is true for all n equal to k. Now we are going to prove this for n equal to k plus 1. We are assuming that the theorem is true for n equal to k. Therefore, A power m into A power k can be written as A power m plus k. Then A power m into A power k plus 1 can be written as A power m, A power k into A equal to, by associative property, A power m, A power k into A. This can be written as A power m plus k into A, which is equal to A power m plus k plus 1. Therefore, the theorem is true for n equal to k plus 1. Hence, by induction, the theorem is true for all positive integers n. Suppose if n is less than 0, we can prove the same result by induction on minus n. That is, n becomes positive. Therefore, we proved that a power m into a power n is equal to a power m plus n for all integers m comma n. And then second property, that is a power m the whole power n is equal to a power m into n. Here also we use the induction on n. Let me start with n equal to 1. A power m the whole power n equal to a power m power 1. Let me simply write this one as a power m. M is m into 1, that is m into n. Therefore, it is clearly true that for n equal to 1, the property is true. By induction, we are assuming that the result is true for n equal to k. That is a power m the whole power k is equal to a power m into k. Now we prove this for n equal to k plus 1. Therefore, a power m the whole power k plus 1 is equal to a power m the whole power k into a power m the whole power 1. That is a power mk into a power m by previous one, that is first part, a power mk plus m, which is equal to a power m into k plus 1. Therefore, the result is true for n equal to k plus 1. Hence, the result is true for all positive integers n. If n is negative, we can prove this result by induction on minus n. Therefore, the second property is also true. A power m into n is equal to a power mn for all m comma n belongs to z. This property can be written in additive notation, that is ma plus na is equal to m plus n into a, and n into ma can be written as nm into a. Therefore, we proved 5 properties for group. Thank you.